origins. The day on which I make this video marks a beginning, a new origin. At the conclusion of each chapter of his book, The Beginning of Infinity, David Deutsch lists different senses in which the phrase, beginning of infinity, can be understood through the lens of concepts explained in that chapter. A beginning of infinity could be the start of some new entity, process, way of thinking or doing, way of moving forward, correcting errors, making progress, solving problems, understanding more deeply or more broadly, being able to do more, to do everything, to show what is possible and achieve it, and see further off still into a deeper unknown of potential discoveries, without limit, except that which the laws of physics mandate. A beginning of infinity is what allows us to make unbounded progress off into an infinite future. But besides what the laws of physics mandate we cannot do, only our imaginations bound what we will make possible. And that, our imaginations, are only bounded by our telling ourselves what is not possible, when in truth, anything that can be achieved really can be achieved given the right knowledge. And the right knowledge begins in our imaginations before being tested against reality. Telescopes can inspire as well as require our imaginations. We can see what we expect in a new way, and it can inspire us. And we can sometimes see that which we didn't expect and cannot yet explain, requiring genuine imagination to solve the problem of what is causing that. Today, NASA released 5 images, the first 5 images from the James Webb Space Telescope, a telescope that is not on Earth, or even strictly in orbit exactly around the Earth, but rather in orbit around the Sun at a distance of 1.5 million kilometres from the Earth, which is about 4 times further away than the Moon is. Hubble, on the other hand, the Hubble Space Telescope, is in orbit around the Earth and is only about 570 kilometres above the surface of it. The James Webb Telescope orbits at what is called the L2 point. When there are 3 bodies mutually orbiting one another, known as the 3-body problem, there are various ways they can orbit a common centre of mass in a stable way. In fact, there are 5 such ways, 5 such solutions found by Joseph Louis Lagrange. So Lagrange gives us the L in L2, and the second of those solutions gives us the 2, hence the L2 orbit. Webb actually orbits around the L2 point in a circle of circumference roughly equal to that of the Moon's orbit around the Earth. And it covers that distance over the course of 6 months, and this keeps it nice and safe from the heat of the sun because, well, it's an infrared telescope and it does its work best when its instruments are kept exceedingly cold. It is, after all, detecting wavelengths associated with warm things, and both the sun and the Earth are very warm and so appear very, very bright to it. The James Webb Telescope has demonstrated over the last couple of days, and will continue to show, what a leap in technology it is over the Hubble. One of the most amazing pictures ever taken by Hubble was the so-called Hubble Deep Field, and then the Hubble Ultra Deep Field and its successors. Here is the first one of those, the Hubble Deep Field. This took 2 weeks of exposure. 2 weeks of pointing the telescope at the same patch of sky, collecting a tiny amount of light hour after hour from that exceedingly dark patch and adding it all together into the single image that you now see. Aside from the pointy things, which are actually stars in our own galaxy, everything else there is a single entire galaxy. Even though theory already told us that this should have been the case, that the universe was filled with galaxies, the observation itself is still stunning, if not surprising. Well, what Hubble did in 2 weeks to gather that image, Webb did in just a few hours, and at higher resolution and detail, even though it is using longer infrared wavelengths. Truly phenomenal. Webb has 4 science instruments on board. It's not merely a telescope with mirrors and lenses as one might think. So when you think telescope in this case, think a finely tuned system of computers, cameras, mirrors, and a whole laboratory on board. It's an unmanned astronomy laboratory more than anything. Its 4 instruments are a part of the entire telescope called ISIM, the Integrated Science Instrument Module. Let's have a look at these 4 instruments and then we'll have a look at the images. The first instrument is called NIRSpec, the Near Infrared Spectrograph. It can analyse light with a wavelength of between 0.6 to 5 microns. A micron is a micrometre, 1,000th of a millimetre, itself 1,000th of a metre. This is longer than usual visible light, which is in nanometres, but never mind that. A spectrograph, an instrument like this, allows us to tell the chemical makeup of whatever light is passed through it. And this tells us not only the chemistry, but also accurate measurements of things like the temperature of the object we're looking at, whether it's the entire object or part of the object. The second instrument is the NIRCam, the Near Infrared Camera. Well, if you're going to have a spectrograph on board that we just mentioned, you might want to collect that light as well. NIRCam does that. It can look at pretty much anything in the universe you can imagine, from stuff in our own solar system through to galaxies nearby, all the way out to the earliest and therefore most distant stars and galaxies that can be seen. Third is MIRI, the Mid-Infrared Instrument. It's just like NIRI, the previous instrument, but looks at even longer wavelengths, like 5 to 28 microns. But this instrument also includes the camera on board, so it's a 2-in-1 kind of a deal, unlike the previous 2 instruments. And finally, the fourth instrument is FGS or NIRIS, the Fine Guidance Sensor, or Near Infrared Imager, and Slitless Spectrograph. This is for precision pointing of the telescope, and in particular an instrument especially geared for the observations needed to analyse exoplanets. So this is why I'm saying it's like a laboratory in space more than just a telescope. But it's not like space telescopes or ground telescopes aren't already laboratories of a kind with other instruments attached to them, attached to what they call the light bucket itself, the thing for collecting the light. But in general, I guess, people outside of astronomy might think, well, these things are just like Galileo's telescope, only bigger and in space. But not quite. It is indeed the James Webb Space Telescope, a whole set of instruments for measuring stuff as well as just observing pretty pictures. And it's the measuring of stuff like the precise wavelengths of light being emitted by distant objects that tells us what they're made of. That is the science of spectroscopy, a phenomenal field of science. We don't have to travel to the stars and take a chemical sample and bring it back to the chemistry labs here on Earth. Instead, we just take a sample of the light, and that has the same information in it. Well, perhaps not all the information, but much of what we're interested in. But if this telescope is taking pictures using infrared light, and our eyes use visible light, how can we see these pretty colours of the pictures it has taken? Well, that's where the processing comes in. There are lots of infrared telescopes that exist already. Many are on the top of mountains. They try to get above the clouds and above lots of the water vapour in our atmosphere, which tends to absorb infrared radiation. So having one in space is perfect because the atmosphere is not getting in the way, nor is the interference from heat from the Earth, from ground-based sources. But because it's not taking pictures in the visible wave bands, processing has to be done so our eyes can make sense of what is being detected. So filters are used and choices have to be made by people. There is therefore a little bit of a fusion of art with science here. Red, green and blue filters are applied to the various wavelengths of light. It's like translating from Mandarin to English. You won't get a perfect one-to-one correspondence between the infrared and the visible pictures that you see, but you certainly can get a very accurate version of the idea. But there is a choice to be made, and, well, there's nothing else for it. We can't see with our own eyes infrared. So to see the truly spectacular, we must translate. And anyways, even if we were using visible light, we would not be seeing the images directly. We never see anything directly at all, after all. Telescopes and eyes are made of stuff that collect photons. We do the job of interpreting photons. This is just another layer of interpreting photons, and we have theories about how that interpretation works so that we know what we're seeing. So if it's said the colours are not real in some sense, in what sense are the colours of Hubble real, or of any telescope real? What does real mean here? All colours, all images, are interpretations of a collection of photons that appear on photographic plates, or CCDs, digital cameras, and computer screens, and that kind of thing. These images exist precisely because human eyes cannot see those objects, whether they be your standard telescopes or your Hubble Space Telescope or whatever. Those objects can't be seen without those telescopes in the first place. All telescopes are, in a sense, adding senses to human cognition, super senses. And this is just one way in which we humans are becoming more and more godlike, or if you don't like that, superhero-like with our technology. In fact, among all of his superpowers, I'm not sure even Superman's vision allowed him to see what the James Webb Space Telescope can. And speaking of that man of red and blue, in these James Webb images, which are coloured, yes, artificially, as almost all pictures in astronomy are, the shortest wavelengths are blue, and therefore they indicate the hot regions. The longest and therefore the coolest regions are coloured red. So let's talk about the first 5 images that have been released by the James Webb Space Telescope. The first image here was taken by NIRCam, and it's of a galaxy cluster. And the galaxy cluster, the technical name is SMACS 0723, and it's James Webb's first deep field. A deep field is, well, a picture that's taken of the very far deep reaches of the universe. Every point there, apart from the things with points around them that look like stars, which are stars, every other point is a galaxy. The stars that you can see, and usually in these situations when you have deep fields and you see things that look like stars, they are stars within our own galaxy in the foreground. And this particular image has also allowed us to see the spectra of a red galaxy. That red galaxy is 13.1 billion light years away. And in that spectra appears oxygen, the element oxygen, which is promising. Oxygen from the first generation of stars, perhaps, which has appeared only 700,000 years or so after the Big Bang. So somehow or other, a first generation of stars had to explode and go supernova, spewing their contents into the galaxy, which we now detect. That's some very short-lived stars, because we know that oxygen was not produced during the Big Bang. There are side-by-side images like this one that show you the same region of space taken by Hubble and now compared to the James Webb Space Telescope at much higher resolution. And here's a video that gives an idea of the size of the patch of sky this deep field represents. It's said to be like a grain of sand held at arm's length, and that would seem to undersell things a little. This is a tiny, tiny patch of sky, and yet, looking at it, there are thousands upon thousands of galaxies, and if you were to zoom in the dark regions between those galaxies, you'd see even more still. The next picture doesn't look like a picture of anything, it looks like a graph. But it's an image of a sort of an exoplanet, and the name of that exoplanet is WASP 96b. It may not look spectacular, but much of astronomy happens to be like this, and we cannot image or see exoplanets directly. We can't take pictures of them because, well, they're too small, too far away, and their light is absolutely swamped by their host star. This graph represents the behaviour of the star's light in the atmosphere of the planet. The star and the planet are 1,000 light years away, and the planet is a hot gaseous giant. The spectra covers infrared wavelengths to a much higher level of detail than we've seen before. And what we're seeing is the transit of the exoplanet, the atmosphere passing in front of the star and the light passing through that atmosphere so that some of it gets absorbed, and what is absorbed is characteristic of what the atmosphere is made of. And in this case, importantly, the absorption spectra shows there's water vapour in that exoplanet. Phenomenal. But it's closer to its star than Mercury is to the Sun. And for someone like me, who was trained on the idea that gaseous giant stars couldn't possibly exist very close to their host stars, observations like this are phenomenal, overturning previous theories. That theory that you couldn't have hot gas giant planets very, very close to their host stars, that theory, well, that was overturned quite a while ago. We started seeing exoplanets very close to their host stars. But astronomy tends to do this. It tends to throw up these problems which require new theories. The imagination of astronomers has to be employed to figure out, how can you have hot gaseous planets, all that gas very close to hot stars, without all the gas being blown away off into outer space by the radiation and the heat? Well, I think much of this is still open to being properly understood. This is a picture of the nebula called the Southern Ring Nebula. also known as a planetary nebula, called so because they were mistaken for planets, because at the center you've got this little bright thing and around it you've got this ring of material. So it kind of looks like Saturn with the rings around a central body. Of course, nothing to do with an actual planet. In the center of a planetary nebula, typically you have a dying star, a star not unlike the sun towards the end of its life, where it doesn't explode, but more gently releases parts of its atmosphere off into outer space. In this case, what we have actually are two stars, one of which is in the process of dying and one of which isn't. They're a binary system in mutual orbit around each other, or rather their common center of mass. The image on the left is taken with near cam, and then the image on the right taken with near cam. So one has the near infrared and one has the mid infrared wavelengths of light, just different wavelengths of light, enabling us to see different levels of detail. We can even see rays of light or beams of light as if coming through a cloud, because that's in fact what's happening. Like the light from the sun as it comes beaming through clouds when there's a break in the clouds, the same sort of thing is happening here, where you can see streaks of light that have come from the central star through the clouds of gas. As you get closer to the star, of course, the gas there is hotter, and as you get further away, the gas is cooler. And you get out so far that you have molecular hydrogen, and around some of this molecular hydrogen can coalesce things like oxygen, so you get rather complicated molecules out there. But near to the star, everything's ionized, so the gas there is ionized and therefore much, much hotter. This is what explains the slightly different coloring, different chemical compositions within the gas cloud, and different temperatures of those chemicals that are there. This is actually the largest image of the series that has been released by NASA from the James Webb Space Telescope. It's known as Stephan's Quintet, or is it Stephen's Quintet? Anyway, the quintet is 5 galaxies that can be pictured here. At least 2 of them are in the process of colliding, but all 5 of them are gravitationally bound together. It's got 150 million pixels and is made up of the composition of 1,000 separate images all combined together. That's how big this thing happens to be. Galaxy collisions like this occur over the course of millions or tens of millions or hundreds of millions, and in some cases billions of years. So we only ever get to see a snapshot. It's not like we get to see them moving as they collide. Hence we do simulations of galaxy collisions inside of supercomputers and then test what our models of those collisions are like by comparing the output of the models with real life things like pictures such as these. If our models are correct, then we should produce inside of our supercomputers pictures that look like this. That's how we compare the theory with the reality that's out there and check our understanding, error correct, and move forward. For me, this is my favourite. This picture of stellar birth. It's the Carina Nebula. Images like this were also taken of the same region of sky by the Hubble telescope, and they were spectacular as well. This is a stellar nursery where stars are being born. You can see towards the top the really bright stars that are there. They were once part of the cloud. They were born out of the material from that cloud. And now, because they're hot, they're pushing the cloud away. The radiation and the particles are literally crashing into the material of that cloud, which is thousands of light years across, and pushing it down towards the bottom of the page. This nebula, this big cloud of gas, is inside the Milky Way galaxy. Compared to the other images we've seen, it's relatively close. It's only 7,600 light years away. Not as close as the exoplanet one, but certainly a lot closer than the deep field. Compared to the Hubble Space Telescope image of the same region, we're seeing here hundreds of stars we have never seen before. There are things here, according to astrophysicists commenting on this picture, that they cannot yet explain, and that is why this is one of my favourite images, because that's exciting. If they can't explain it, they're going to have to come up creatively with new ideas, perhaps some new astrophysical theories to explain what the heck we're seeing, or at least the repurposing of old astrophysical theories in a new way that hasn't been done before. Whatever the case, it's going to take creative problem solving from the astrophysics community to figure out what's going on here. The scale of an image like this is just hard to get across. But certainly if you were to take the entire solar system all the way out to the orbit of Neptune and to put it into that cloud somewhere, you wouldn't see it. It wouldn't show up as one pixel. That's how massive this thing happens to be. Looking ever closer at images like this, or taking images like this of other parts of the galaxy and other parts of the universe, are we going to see evidence of alien civilizations in any of these images, or ever? We can't know now. We do know that look-back time is a thing, so perhaps we could see evidence of an alien civilization here if only we knew what we were looking for. But the deeper into space we look, the further back in time we are seeing, because the light reaching us is that much older. It has taken so much longer for that light to reach us. So if we are looking at a galaxy 12 billion light years away, and we can see hundreds of billions, perhaps trillions of those, we are also seeing them as they were 12 billion years ago, which would be a mere 1.7 billion years or so after the Big Bang. This means that if we want to see evidence in those galaxies of alien civilizations, those civilizations would need to come from quite possibly a first generation of stars made solely of Big Bang material, consisting only of hydrogen and helium. And then, after those stars go supernova, we need the time to wait for those clouds of gas and enriched material to come together. But as we've already seen, there is that spectra of a galaxy 13.1 billion light years away that contains oxygen. However, in what form is that oxygen? Is it just floating through the gas of that galaxy as a nebula? Presumably so. So what we need is not only the oxygen, but carbon, nitrogen, and all those other elements on the periodic table that are typically associated with life, or at least could form molecules complicated enough that could arrange themselves into a self-replicating molecule of a kind, so that we could get the process of life going. Hydrogen and helium won't do it. The hydrogen's too simple, helium's too inert. So we need the enriched material of these other elements to be detected in those distant galaxies. But more than that, we need to wait for that material to then coalesce once more into new stars and planets, especially rocky planets on which presumably life can begin and then evolve and then become intelligent and then become civilized. Here, in this part of the universe where we now find Earth, it took about 13.7 billion years for all of that to happen. Generations of stars had to be born, go supernova, die, and then recoalesce into new stars and planets before the chemistry was just right. And then, once the biology got going, it was still 2 billion years of nothing but bacteria before the complex life began to evolve. Even if we cut all of that time in half, or even by a factor of 10, should we expect to see intelligent alien life, or the signs of intelligent alien life out there? I don't know. Perhaps we should be optimistic. Are there other processes we do not yet know about that can lead to complex chemistry and biological evolution? If we don't know about any such processes now, how can we search for signs of it? What would we look for? But telescopes, like the James Webb Space Telescope, exist to do precisely this. Allow us to see both what we were looking for, somewhat like a metal detector on a beach, but also now and again to reveal the unexpected treasure, the thing that we didn't expect to show up. So what we really want in our images is that which no existing theory can explain, but which is nevertheless evidence, a clue, a hint that something is perhaps wrong with our understanding of the cosmos, and that then leads to creativity, the attempt at a solution. The crucial component of the scientist is then needed, the thinker, the imagination of an entity that can traverse the set of all things that can possibly be imagined by adapting what we know and taking into account what we do not yet know to form a new but coherent picture of our underlying reality. The James Webb Space Telescope is just the beginning, as will its successor planned for launch in 2035 be also. And the name of that telescope? Origins. We are always just at the beginning, merely scratching the surface of the unknown and revealing more of what we do not know. And the thing about the unknown is that by definition, it's unpredictable, unforeseeable, ahead of time. Only by comparing what we know to what is out there in physical reality do we ever encounter a problem with our knowledge, by which we mean a conflict between what we know as our best explanations of reality and the reality itself. Telescopes bring into view not merely what we expect, but also those crucial observations that are problematic, those things we cannot readily explain. And that's where we come in, not merely our telescopes. That is where people, creatively, must guess the mechanism behind the image, the thing not seen in those images, the unseen cause of the seen effect. For this is what science does. It explains the seen in terms of the unseen.